I'm gonna study until I pass out. Ah! Ah! Till I pass the freak out. God.
Mm-hmm. Okay. You see the board? Yeah. Okay. This chapter, the exercise related about the electric field. And look at the one. Okay. This is the option. The multiple choices.
This
The
one
force
I
between
already
two
know
identical point
how
charge
to
x, y, and
do.
its force is F. Charge x is double. Charge y remains same. And we just want to know which row of the table gives the force on each charges. Or force.
The distance between proton and electron is r, the electrostatic force is F. Distance between the proton and electron is doubled. So D.
I don't know. Attraction. Oh, and repulsion. Yeah, repulsion. Okay, the two types are included in the electrostatic force, right? Okay, the distance between the proton and the electron is double. Which row? Which option is equal to the electrostatic separation? Choose which one. Maybe we can use Coulomb's force, the formula. Yeah. So, use the formula. The final answer. It's D. It's D. Why D? Because the distance is doubled and distance is squared. Yeah. So it's 2 squared. It's the radius.
I'm
Is
correct.
the denominator, right? Double the denominator. Okay, and r squared will be the 4, right? And with the 4, so the factor will be 1/4, right? Yeah. Okay, so the final answer is right. Okay, look at the question 2. A potential difference is applied across the two parallel plates. A particle carrying a charge of the 0.1 coulomb is placed between the plates and experiences a force. The distance between the plates is halved, and the potential difference remains constant. Which of the following is now equal to the electric field strength between the plates? Okay, the question just one.
Okay, this is the one that's hard. Potential difference is applied across two parallel plates. Particle carrying a charge of 0.1 is placed between the plates and experiences a force F. Electric field strength. The electric field strength with the distance being normal is 10F. Okay? The electric field strength with the distance halved. So E equals V over D. E equals V over D, right? V equals F over Q, V equals V over D. I mean, F E equals V over D, E equals F over Q, E equals V over D. Now D is halved, so if D is halved, E is doubled. If E is doubled, then E is 10F, doubled is 20F. So it's 20F.
Asked to calculate the electric field strength. So maybe we can use the electric field strength formula. How to calculate? Right. Okay.
V over D, F over Q.
Mm-hmm.
Let me write this out. All right, I got it. E equals F over Q equals V over D. V over D, distance is halved, so E is doubled. Since E is doubled and we're representing E and F, then we use the charge to calculate 10F times 2 is 20F.
Right? We know the Q equal 0.1, right? Right? Yeah. Okay. And we can use the force equal the Q times the E, right? And we know the Q, that is the 0.1. So the E equal. So the electric field strength will becomes double, right? Will become double of the original one, right? The new electrical field strength. And tell me how to calculate the final result. Use
The general to-do list for today is today's to-do list is to watch all the quarantines. Okay, I know what the to-do list today is. I have it in my head, drawn out in my head.
what we have right on the board information. Then tell me the first step what we need to do. Double. And the original one is the 10F. Okay, so now becomes on the double. So will be the 2 times the 10F, right? So the between point X, okay? So the distance is half. The point D is which of the following shows the corresponding variation of electric field strength with X? Okay, the graph.
B.
The graph. We need to find the potential and access to know what?
V over X is the electric field strength.
To know what? From the graph. The voltage over X graph. What we can learn from it? What we can know? The gradient, the area, or something else? Represent the electric field strength. Choose which one.
Sure.
The E is the slope from the graph, right? Because the gradient is negative or positive?
Negative.
Okay, negative. So choose that. Right?
Yeah.
It's like how dense, the keyword that is how dense, that is how strong or how weak the field, right? So that is the main idea of the electric field strength. Okay, and how about 7.3 electric force?
It's the product of the two charges over the radius, the distance squared.
So the force we always call it Coulomb's force, right?
Yeah.
And the formulas is right there, right? The force that is the proportional to the product of the two charge, right?
Yeah.
And inversely proportional to the what?
The distance squared.
Yeah. Okay, no problem. And how about the next section? 7.4 electric field due to a point charge, which means the point charge will produce electric field. And how's the formula?
Electric field strength due to a point charge. F over Q, right? I have my notes right here. Due to point charge is okay, a single charge over the rest of this stuff. 4 pi ellipse I forgot the name of it, but permittivity of space times r squared. Electric field and potential. Electric field strength with potential is F equals V over SR. Electric field between parallel plates is E equals V over D. Electric potential for radial field. I don't know what that is.
It's like
Forgot.
okay, and
Electric field due to a point charge is the single charge over 4 pi permittivity of space r squared.
let's quickly review it. And due to the point charge, we can use the formula, the force over charge, okay? And the result, we can use the E, right? The E is the field strength due to the point charge, right? And use this formula. Substitute the force into and the K, product 1, product 2 over R squared, okay? And over the Q1, right? So the final result, that is the Q, O2, right? Charge 2 over R squared, right? So the final result, that is the formula of electric field due to the point charge. Understand that?
Yeah.
Okay. And 7.4 tells what? Potential. What is the definition of potential? It's like a voltage, right?
Yeah. Yeah.
Potential.
Yeah.
What is the definition of potential?
The joules per coulomb.
Joules per coulomb.
Potential is the work
Maybe you can use some other
done
words to describe it. Maybe you can use some formula.
over
I don't remember
unit
the formula.
charge.
And the last lesson, I just used the equation and the energy, electrical energy equal the charge times the potential difference, right? The potential, okay? Right?
Yeah.
And the potential, that is the electrical energy over the charge quantity, right? So we can use the fraction to define the electrical potential, right?
Yeah.
It's like electrical energy per unit charge, like electrical energy per the charge, right? Okay. Understand that?
Okay. Yeah.
Okay. And the next formula, that's the 7.6, the electric field between the parallel plates. In the parallel plate, what do we produce in this environment?
E equals V over D.
Uniform
Uniform, yeah,
electric field.
yes. The uniform electric field, just like in the environment, right? And everywhere, every point in the environment, we have the same direction or same magnitude of the electric field, right? Like here's the two parallel plates. Okay. Maybe we can suppose that the left one is the positive and the right one is the negative. So we can draw the electric field lines, right? Like this. Every single lines and parallel, right? Okay. And in this distance, right, in the two parallel plates, we have the same E. The E, that's the electric field. And the everywhere in point, okay, the every in point, we have the same magnitude and direction. The direction is from the left to the right, right? Left to the right, the electric field. Understand that?
Yeah.
Okay. And then the final one is the 7.7. It's about the electrical potential for radio field. Radio field. The radio field, maybe we can use the two different charges. Like if we want to draw the positive charge and put the left side and the right side and negative. Okay. And we just want to draw the radio field. And how to draw it? The left one is the positive charge. Positive charge. And the right
Radio
one is the negative charge.
field.
How to draw the radio field? How to draw it?
The middle is the straight line.
Yeah, it's really nice. From the direction, just from somewhere to the another where.
Positive to negative.
From the positive to negative, right? Okay. Okay, the arrow, how to label arrow?
In the middle.
From the center of the positive charge to the infinity direction, right? Okay. And in purpose to virtue the more, and we can draw just 1, 2, 3, and 4, and 6 lines, right? Probably we can just draw another. We also know the force that we call the Coulomb force, right? Okay. And the 7.4 is about due to the point charge, how to draw the electric field. And another, we have also know the potential. And finally, the parallel plates produce the uniform electric field, right? Got that?
Yeah.
Okay. After that, we can take some exercise. Okay, I will put. Wait for a second. Between the two identical point charges x, y.
Now we can get to this point.
Last lesson, we have just learned the electric field. And this lesson, we're going to learn the capacitance. Okay. Have you ever remembered the capacitor? What is the capacitor? What is the capacitor?
Forgot.
Forgot, right? Okay, here's capacitor is always the electric devices. We always use just the tool to store energy, to store what energy, the electrical energy. Okay, so sometimes we also use the tool to store
7.9.
energy, and after we store energy, maybe sometimes we can use it to discharge the energy, right? Okay, so here we have the two process with the capacitor. The first process that is we can use it to charge the capacitor, to charge the stored energy, right? The electrical energy. And after we have charged the energy and we can use it to use the electrical energy. Maybe sometimes we can use the capacitor to discharge the electrical energy. Okay, so we have the two process, right? Understand that?
Yeah.
Okay, so capacitor we can use to store energy, or we can use to discharge the energy, right? And the symbol is like this: the two parallel plates. But I have a question: is there any current in the middle? In any current in the middle, the battery always use the capacitance.
Yeah.
Okay, and the unit.
Capacitance is charge over voltage. Oh, this is a lot. This is a lot. It's the charge per unit potential difference. This is really hard to interpret.
Unit. Remember the unit. The unit, the capacitance unit is F. Okay, no force. The unit is F. Okay, understand that?
Farad, right?
Is there any problem?
No.
Hello.
Yeah, no problem.
Okay, and look at the, for example, a parallel plate capacitor has a capacitance of the one. Okay, here's the nano farad. How to transfer nano into farad? Nano farad into farad.
Farad. Variable plate capacitor has capacitance of 1 nanofarad. It is connected to voltage supply of 0.3 kilovolts. Just write out the equation. Got it.
Nano farad.
E equals Q over V.
And the potential is what? Potential.
0.3 times 10 to 3.
Or maybe you can write the 300, right?
Yeah.
300. Okay, so the Q, the final equal, the C times V is the 300 and times 1 times the negative 10, right? So
Yeah.
maybe you can use the 3 times 10 and negative 7, okay?
Yep.
The unit is what? Physical unit is what? Of a charge.
Micro.
Micro, the C, right?
Oh,
The unit.
Yeah.
Okay, C, right? Okay. After that, okay. And after we have now the capacitance is what? And what's the definition of the capacitance? Okay, and how to copy the electrical charge quantity, right? And we need to copy the energy. Okay, the electrical energy use the capacitor. If we want to
I
charge,
gotta take a shit. I know this stuff. Who did this to my computer? Gosh. Spaceberry smoothie, boy. Yeah, boy. Boy.
Charge capacitor. So we need the power supply. Like power supply, the process just like the power supply pushes electrons to one of the metal plate, right? And in this process, the wheel does the work on the electrons. So they will produce the electrical energy, right? Understand that?
Yeah.
Okay. So in this process, the main target is another knowledge. The first knowledge we have learned the charge.
The energy stored is QV. The capacitance is C equals V. Q over V. Capacitance is V over Q over V. Energy is 1 over 2 QV. Oh my god.
The more information about the potential. Potential difference or charge. So we can choose the first one, the 1 over 2 and times another form and write by this. Okay, look at the example.
Calculate the change in energy stored in capacitor. Capacitance 1,500 microfarad when the potential difference across the capacitor changed from 10 volts to 30 volts. So we have W. Calculate the change in energy. W equals 1 over 2 CV squared. 1 over. Okay. Answer is 0.3 joules. Let's see if we're right. 0.3 joules, yes. This is the energy. No, Q 1 over 2 QV. QV 1 over 2 QV. Okay, with the gradient we can find 1 over C. V equals Q over C. C over Q over V. Yep. Yep. And then we have this. the resistance is high, the current will decrease more slowly, and the charge will flow from the capacitor plates more slowly. Take longer to discharge. Resistance low more quickly. Yep, got it.
Okay, I will send the notes to the group.
All right. The final video.
Hello. Okay, I can hear you. And you finished. Let's take a quick review. Last two lesson. The first lesson we talked about the electric field, right? Okay. And second lesson we talked about capacity. So, what is the capacity? Remember? You remember?
Capacitance is the energy stored due to the energy stored due to charging of charge, due to the storing of charge.
What is the capacity?
Charging or discharging.
Okay, yeah. You just mentioned that they have the two processes, right? The first process is to charge the energy, right? Charge the capacitor energy, and the second process is to discharge the energy, right? Okay. And we have nerd. If we charging or discharging, then we have the three different graphs, right? The first graph is the current, related about the current. Second graph is related about the potential, right? Potential difference. The second and final one is related about the quantity, right? Charge quantity. Look at this. Okay, the three graph, right? Okay, and you can tell me the three graph is the process charging or discharging.
This is
it charging or discharging?
Charging.
it's charging.
Discharging. Why discharging?
No, not discharging. It's charging.
Okay, it's charging. Why? Because we can see, and if the battery charging energy, right, charge the capacitor. Okay, and we know the current will decrease, right? Will decrease like exponential decrease, right? Okay, so we can see from distinguish from the current and time graph, right? Okay, understand that?
Yeah.
And the potential difference and the quantity is increasing, right? It's increasing because the capacitor will get in the electrical energy, will get in the potential difference, okay? And same time they will get in the charge, right? Charge quantity, okay? Understand that?
Yeah.
Okay. After we have another charging, okay, and we are going to another discharging energy, okay, like the circuit, the closed loop, the closed circuit, okay. And here's the battery, okay. After battery releasing all the electrical energy to the capacitor, and the capacitor has the full energy, okay, for the electrical energy, okay, energy. And if we switch to the point P, okay, switch to the point Q, okay, and which means collector
Point Q would be discharging.
and you can see
point
the
P
right side
would
is
be
like the
charging.
closed circuit, right? The loop. Understand that?
Yeah.
Okay, the loop and difference and the charge quantity and all are exponential decay. Why exponential decay? Last lesson I told you. And you asked me the same question. Why the three graphs all exponential decay? The exponential decay curve. Think about it.
Because it's discharging, and then the voltage will decrease, and the charge will decrease because it's discharging.
Okay, because they are discharging, so the approximately the shape like the exponential decay. Okay, the decrease line. And I just want to say when the capacitor discharges through a resistor. Okay, through the resistor. When the capacitor discharges through the resistor. Through a resistor, like the graph, through the resistor. Okay, here's the resistor, through the resistor. And first, the voltage across the resistor is high. Okay, at the beginning. At first, the voltage across the capacitor, right?
At first, the voltage is high.
It's okay.
Yeah.
Okay. At first, the potential of the capacitor is high. Okay. So then we have so we have a large current flows, right? So we have the
Large current flow due to high
flows. Okay. And as the moment as the charge leaves the capacitor and its voltage decrease, right? Okay. As the charge leaves the capacitor, its voltage decreases, right? Understand that?
Yeah.
Okay. And the lower voltage means a small current, right? So the charge leaves more slowly, and this causes the voltage to drop quickly, right, at the beginning, and then more gradually over the time, right? So we can use the mathematically. The behavior flows are exponential decay function, right? So the graph is like the exponential decreasing curve. Understand that? Right?
I'm confused why for charging the current is also decay.
Why the charging is also decay, the potential or the quantity, right?
The current.
The current is that process
because the rate of charging decreases.
Yeah.
And we know that the energy stored in the battery is limited, right? Is limited, right? At a long time over, and all of the electrical energy will flow to the capacitor. Okay, at the beginning, okay, the current is maximum, right? The current is maximum because the all energy, all electric energy is stored in the battery. So at the beginning, so the current has the maximum, right? Has the maximum, right? Okay, and a long time over, the all electric energy will flow to the capacitor. So that will cause the battery has the low electrical energy. Okay, so if we have the no electric energy, the no current, right? So the current that will be the approach to zero. Okay, and in the process, in the charging process, the current flows like the exponential decay curve. Okay, because the current flows to the capacitor, the process like the charging process, the electric energy will flow to the capacitor quickly. The charging process, the time is so quick, so the current will decrease so quickly like the exponential decay, right? Understand that?
Yeah.
Okay. So remember the set graph. The first charging graph, the very particular, the one is the current time graph. Okay, and the other two one, the voltage and the charge quantity, like it's like the charging process, the increase, right? Okay, increase to the maximum value, like the exponential decay, right? Understand that?
Yeah.
Okay. So remember the set graph. The first charging graph, the very particular, the one is the current time graph. Okay, and the other two one, the voltage and the charge quantity, like it's like the charging process, the increase, right? Okay, increase to the maximum value. And but the current time graph, like the exponential decay. Okay, and in the charging process, all three graphs are decreasing exponential decay. Understand that?
Yeah.
Okay. After that, and look at the summary. Okay, the discharging, we can summarize that. The discharging curves all identical, and the current decreases for the charging process, but increases for the potential difference and the charge the stored original value. Original value represents the electric energy.
Okay, today this one is bleh. This video is learning time constant. I'm gonna take a break. My brain is kind of dying. Need to stay strong. Stay strong. Need to stay strong. Time constant for discharging capacitor is down to 37%. For charging capacitors, is up to 63%. Taken for charge or potential difference. Current, potential difference, or charge. Okay. Greek letter tau. Measured in seconds. Time constant. Resistance times capacitance.
Okay. And can use the mass formula like this one.
Exponential discharge equation. Charge equals initial charge value times exponential function to the power of negative time over RC.
Like this one. Okay.
Natural log.
If t is 2 seconds, okay, and we can take into and we can get in right? 2, 3. Understand that? Remaining charge, right? The remaining current. Okay. So
Okay, let's do the worked example. Ten mF capacitor is fully charged by a 12V power supply and then discharged through 1K resistor. What is the discharge current after 15 seconds? Discharge current. We're trying to find the current. We have the resistance and so this is discharging, so the initial initial potential difference is the maximum potential difference. 12 volts equals IR. Fifteen seconds times over RC. R is 1000 times 10.
the remaining potential is another method about the mass, right? So we can use the formula to change the remaining quantity, the gradient.
Negative 1 over RC.
Okay, the gradient is -1. Okay, so remember the formula, right? And the straight line, the gradient is negative, right? Okay, because here's the negative, right? Understand that? So
Yeah.
if I want to find the RC, the time constant, how to use the graph to do it? How to use the graph to do it, to solve it?
Find the gradient.
Find the gradient, good. Yes, I want to use the gradient. I want to use the graph. The first, I want to use the graph to find the time constant. The first thing you mentioned that we can get the gradient, okay? And how to use gradient to get what? To get the time constant. How to use the gradient to find the time constant? The gradient is m, right? So the m is negative RC. Okay. Okay. And the x-axis is the time. Okay. And use the topic just want us to use the graph to determine the initial voltage across the capacitor. Okay. How to solve it? How to solve it? How to solve it? The y-axis has changed the login V. The V is the potential difference. Okay. So the equation above the graph, here's the equation. Which equation that we might use?
The first one.
Okay, the first one. That we might use the first one. And the first one is login V equal the negative 1 over RC, right? And times T and plus the login delta. Okay, login delta V. Okay, so how to use the graph? How to use the graph to find the initial voltage, not time constant, exponential. Okay, axis. Understand that the topic? Is there any problem?
No problem.
Okay, so the discharging process that we have transferred the exponential decay into log equation. Okay, a log equation can be written as the linear straight, right? The straight line. Okay, the straight line that we have the gradient and intercept with y-axis. Okay, so here is the three equation. Okay, the first one and another one is the log Q, right? Equal the negative 1 over RC and times T, right? And plus the gradient.
All equal.
Yes, ultimately equal. Okay, equal gradient value, right? Okay, but which variable is not equal? Which variable is not equal from the graph?
The intercept.
Yeah, different intercept with y-axis. Different intercept with y-axis. Okay, understand that?
Yeah.
Right? Okay. And finally, here is the graph that tells us, okay, to mention. The first, the gradient of the straight line is given by the -1 over the time constant, right? And the second, their y-intercept with the line represent the initial login charge quantity or initial potential difference, right? Login, right? And the login initial current, right? Understand that?
Right.
Okay. So this is the chapter, okay? It's the two chapters that we have done, right? And the content, look at the content. Okay, the content, okay? The content is about capacity. Okay, quick review here. The first will be the charging process. Okay, if we finally that we can use this equation to analyze the result. Understand that? Right?
Yeah.
Okay, no problem.
No problem.
Okay, so this is the one that you are available for studying is what? And how's your here's the attempted line, right? Here is
Yeah.
the approach to the 3. Okay, and the reason why you don't write it?
I don't know why.
Okay, the question just want us to explain why movement of the diaphragm causes the potential difference, the signal across the resistor R. The resistor R. You can see the diaphragm movement causes the voltage. See the graph? When the diaphragm, and we can write it in this form. When the diaphragm moves, okay, and capacity change or not change?
I'll change it.
Okay, yes, the C changes. Okay, and we can use the formula because the charge quantity, the Q equal what? Equal what? The charge quantity equal what? Equal what?
I'm not sure.
The C and V, the product, the capacity times the potential, right?
Oh, yeah, yeah.
Okay, so the charge quantity that changes, right? Because the capacity changes, so the charge quantity changes, right? Understand that? No problem?
Capacitance changes. Charge changes.
Wait.
Because you just see the C changes, right? The C changes, the capacity C changes, right?
Yeah, the C changes.
The C changes, and the V
Okay.
is constant.
Is the charge constant?
Charge constant, the 3. Understand that? So the charge quantity, right? The V, the potential constant, right? And the Q, the charge quantity that changes, right? Understand?
Wait, which one is constant?
The potential V. The V. Because the topic just told us the V is the 3, okay?
Oh.
Okay, so the charge quantity will change, right?
Yeah.
If I change the capacity, so using the formula, the charge quantity, the charge equal the product of the capacity times the potential. So I change the capacity, so when the potential constant, so the charge quantity that changes, right?
Yeah, charge quantity changes.
Okay, charge quantity changes. Okay, and the charge flow through resistor R, right?
Yeah.
And so a voltage. So a voltage. So a voltage, we use the ohm law, right? The R, the I, and times R, right? Up
Yeah.
here, appears cross R, right?
Yeah.
Understand that? So we can write in this form. Okay. Understand now?
But when the charge changes, how's it change? Like, is it changing in the capacitor?
Yeah, in the capacitor.
So it's discharging.
Discharging not discharging.
Okay, is it discharging? Like,
You see in the process, this process is discharging.
oh, okay.
The same, right? And this question, look at this. The circuit below model a single taxial of the CCD device. The photo cell, here's the photo cell. Okay. The photo cell generates a voltage that depends on the intensity of the light, right? Intensity of the light falling on it. When information about light intensity is required, the switch is open, okay? And the voltage across the capacitor at an instant can be read out into an electronic circuit represented by the voltmeter at a later time. And the topic, you use the formula to copy the charge, and the Fred is right. Okay, and the mile voltage, right?
Yeah.
95. Okay, so use it right, no problem. The two. When don't run this?
I don't know why it stays. Like, I don't know why the voltage stays for some time.
the voltmeter reached the 95 mile voltage for some considerable time. And the question, let me say what this tells you about this voltmeter. Okay, it tells you about the voltmeter. It's like for some considerable time, which means maybe the resistance is high or low. It's high or low.
Higher.
Yes, higher, which means no current drawn, right?
Yeah.
Okay, so we can see, we can write this because this question has a high, very high resistance. Understand that? Okay.
Not sure why. Why does it? Why is it? Because like why the high resistance causes the delay?
Look at the voltmeter. The voltmeter reads the 95 mile voltage for some considerable time. And in the topic, the circuit below, and I see the voltage of course the capacitor at the instant can be read out. If I keep the voltmeter, the reading keep the 95 mile voltage, right?
Yeah.
Keep the value. If I keep the value, which means the voltage keep constant, right? If the voltage keep constant, so which means the capacitor is charging or not charging? Is charging or not charging?
Charging.
No. Why not charging? Because there's no potential change. Why charging? Think about it. The voltmeter reading remains unchanged, right?
Yeah.
The voltmeter reading remains unchanged for a considerable time, and that will means the capacitor hardly discharges, right? Understand that?
So it charges later.
Which means the capacitor hardly discharges, right?
Yeah.
Like you think that the potential, the voltmeter reading remains unchanged, right? Remains unchanged for a considerable time. Which means the capacitor must be hardly discharged, right? Hardly discharged. Okay. That indicates the voltmeter has the very high resistance, right? Because if we have the very high resistance, that will result in extremely small leakage current in the circuit. Okay. Right? So the charge, you think about if the phenomenon happens, the charge on capacitor streams very slowly, right?
Yeah.
So we can keep the voltage stable for a long time. Understand that?
Okay. Yeah.
You think about it for this angle. You think that if I want to voltmeter, the reading keep it constant, right? Keep it constant. Okay. So if I keep the constant of the voltmeter, the reading keep it constant, unchanged, right? That means the capacitor can be discharged, right? Understand that? If the capacitor discharged, the potential will decrease, right? The keyword is important because the another current change, which means that we have a very high internal resistance. Okay, change the way unchanged.
Yeah.
Like you think that the potential, the voltmeter reading remains unchanged, right? Remains unchanged for a considerable time. Which means the capacitor must be hardly discharged, right? Hardly discharged. Okay, that indicates the voltmeter has the very high resistance, right? Because if we have the very high resistance, that will result in extremely small leakage current in the circuit. Okay, right? So the charge, you think about if the phenomenon happens, the charge on capacitor streams very slowly, right?
Yeah.
So we can keep the voltage stable for a long time. Understand that?
Okay. Yeah.
You think about it for this angle. You think that if I want to voltmeter, the reading keep it constant, right? Keep it constant. Okay. So if I keep the constant of the voltmeter, the reading keep it constant, unchanged, right? That means the capacitor can be discharged, right? Understand that? If the capacitor discharged, the potential will decrease, right? Understand that?
Yeah.
Okay. If the capacitor potential will decrease, right? Understand that?
Yeah.
Okay. If the capacitor discharged electrical energy, the potential must be decreases, right? Okay. The graph. Okay. Understand that? If in the discharge process, the potential with the time increase, the potential will decrease, right? But the voltmeter unchanged, right? So the V unchanged. Okay. If the V unchanged, so which means the process is not discharged, right?
Oh yeah.
Okay, it's not discharged. Not discharged, which means there's no current change, right? No current change, right? Understand that?
Okay. Yeah.
There's no potential change, right? No potential change, and must be no current change, right?
Yeah,
No
yeah.
current change, that has the very high. Has a very high internal resistance. Okay.
Okay.
Understand that? Very
Yeah.
high internal resistance. So we can see the voltmeter, they keep the constant, right, for a long time, and we can keep the voltage stable for a long time. Understand that?
Yeah.
Okay. Okay, so we use the potential unchanged to get the this is not a discharging process. Okay, in the not discharging process, that means there's no current change, right? No current change, which means using the Ohm law, right? The Ohm law, okay? No potential change, no current change, which means that we have a very high internal resistance. Okay, understand that?
Right, yeah.
Okay, so if we have a very high internal resistance, that will result in extremely small leakage current, right? Understand that? So the charge on capacitor transfers slowly. Okay, and this is the purpose of to keep the voltage stable for a long time. Understand that right now?
Yeah.
Okay, no problem. Is there any problem? This question?
Oh no.
Okay, and in this graph, you calculate, right? Use the discharging equation, right? And this is the graph. Okay, that's a field line, no problem. Here's the intersection with the y-axis, and you use it to calculate the slope, right? The gradient. And the topic just want us to explain how the graph shows the voltage decrease exponentially. Okay, you see what?
Because the Ln values decrease linear, so the actual values should be exponential.
Okay, no problem. This one got the 1 mark, and the value decrease like the exponential, right? Get the 1 mark. Okay, no problem. And the question 2, find appropriate value for resistance of the second voltmeter. How to calculate? How to calculate? You don't know how to calculate?
No, I don't know.
You have the graph. So how to use the graph, or use another question to calculate the graph? How to use the graph to calculate? The graph, you have the intercept. The graph, you have the slope.
Yeah, intercept.
Yeah, then we might use the intercept. Okay. How to use the graph to calculate? The question is want us to find the appropriate value for the resistance of the second voltmeter. The second voltmeter, the resistance of the second voltmeter. Okay, the second voltmeter. How to use it? Think about it. Why?
I think we can turn it into a
We want,
equation.
we want the resistance. We want the resistance. Resistance. You remember the time constant? The time constant? The time constant is what? It's a product of resistance times capacity, right?
Oh yeah.
Okay, in here equation, then we can get the resistance. Okay, use the time constant. Okay, to over what? Capacity, right? The time constant is what?
Yeah.
Time constant. How to get the time constant? Use the slope or something else. The slope. Time constant. How to get the time constant from the graph? Time constant. Don't forget the equation that yesterday we have done the formula. The gradient represent what? The gradient represent what? You need to write the equation form. And here's the form. The y is log in, right? The log in v, and the x is t, right?
Yeah.
And the gradient is the -1 over rc, right?
Oh yeah.
Okay, and plus the log in, right? With the law. Okay, so we can use the graph you plot to get what? To get the gradient, right?
Yeah.
Okay, the gradient might use the change in the delta y, okay, over changing the delta x, right? Understand that? The delta y over delta x, right? To get the gradient, okay? The gradient represent the -1 over rc, right? Here rc is the time constant, right? Understand that?
Yeah.
Okay, so if I got the gradient, okay, and after that, and we can solve the resistance of the second voltmeter, right? Understand that?
Understand.
So the first step, you have to calculate the gradient of the best field line you plotted, right? And second, using the gradient represents the -1 over rc, okay, and the rc is the -1 over the gradient, right? Okay,
yeah.
And take the gradient value into, and we can get the rc. Use the rc to get the resistance, right? Calculate to over capacitance, so we can get the resistance. Understand now?
How do you get the capacitance?
Capacitance from on the graph, capacity, and use the sketch graph we have seen if he had watched the ammeter 2, where the capacity equal 0.22. Okay, right?
Yeah.
Understand? Okay. The question 3. Use why is what the charge is being stored in the capacitor, and this is what, and as it reaches the maximum capacity, this is what the current decreases, right? Is you right? This is the current, the word.
Charge is being stored in the capacitor, and as it reaches the maximum capacity, the current decreases. The charge is being stored in the capacitor.
This one is what? Right? The current.
Yeah.
The current decreases. And the question wants us to explain in terms of the charge, using the charge to interpret what happened in the circuit. And this is the charge explanation, right? So the capacitor in the charge process. Okay. So the current that will decrease, right? Here get away the 1 mark. Okay. And the curve. So here's the 3 mark. Here's we get the 1 mark, and the energy store get the 1 mark. But have another 1 mark we don't get. And you think about how to get another 1 mark. How to get another 1 mark? Another 1 mark refer to what? Maybe the shape, right? Maybe the shape of the graph, right? Because the graph is exponentially, right? Decreases exponentially, right? Understand that? Exponentially. You need to write this word. The keyword is important because the another mark is for the exponentially to describe the tendency. Understand that?
Okay.
Okay. Because the decreasing process is exponentially decreases, not linear decreases. Okay. So we need the word exponentially to describe the shape, decreases shape. Understand that?
Yeah.
Okay. It's another mark. So we can get the 2 mark. And explain what we have seen if he had watched the ammeter 2. Ammeter 2 is what? Ammeter 2 is right.
Yeah.
No difference because they are in the same circuit. Ammeter 2. Here's the 2 mark. Why no difference? Why no difference?
Are they not the same series?
Because the collector of the x, right? And in there's the no current change, right?
I think they should be the same. The same.
Okay, no problem. It's the same. The 1 mark. Yeah. And here's the no difference. Okay, no problem. And use the sketch graph to estimate the charge. Okay, estimate the charge, which has passes through the ammeter 1 between the time 3 to the 10. Okay. Which formula you use? Which formula you use?
Trapezium.
The capacity. This one. The charge quantity over the V, right? This one.
Oh.
Right.
I use the graph.
Use this one. This one, the graph. The current, because we have the EMF is 1.5 voltage, and the charge quantity is what? Charge quantity is what? You copy this charge, right? So charge is the 63 mil capacitance, and the C taking into right, and the 21 U front, and the graph. Okay. Oh, the charge right. Yeah. Okay. Use the graph is correct. No problem. Okay, understand that.
Yeah.
And another one. Use the graph
Yeah,
you
right.
answer about the estimate. The capacity. So the 4.2 is over 1.5. Mm-hmm. The battery, look at the EMF is what?
0.5.
No, it's 3 because each cell, there are two cell. Look at the one cell is 1.25. This one is 1.5. So together, it's 3. Understand that? 3 voltage. Mm-hmm.
Yeah.
Okay, because the topic tells the each cell has an EMF of 1.5 voltage. So this cell 1.5, another cell is 1.5. So together, the total EMF, the total potential, right, have the 3 voltage. Okay, so we have to change the 1.5 into the 3. Okay, understand that?
Okay.
So the answer is what now?
2.1.
Okay, 2.1. Okay, so be careful. Look at the keyword, right? This one. Understand it now?
Yeah. Okay. Got it.
And stay. Okay, stay. Get 1 mark, and S plan get another mark. And the stay and S plan he will observe each emitter if he didn't continue the experiment by moving the collection X from L to M. Okay, from L to M. You don't understand this topic? The question? From
I
L.
know that the EMF is now 3.
So the X is from L to the M. Okay, so what changed? What will change?
The EMF increased to 3.
Okay, yes. So the current the current has the opposite direction, right? Opposite direction, right?
Wait, why?
So the current has the opposite direction, right? For A1.
Wait, why?
Because if you collect this one, collect this the point, if the A2 switch to the M from L, and the current, right? The current for A2, what will change? The current, what will change?
Double?
Why double?
Because EMF is doubled.
Let me think. If I switch from X to the M, switch to the M, if I switch to M, and what will change? And here's the line, right? Here's the line. And this is the current from the current flows, right? To the M. M of the, where's the M? Think about it. When X move from L to the M, the battery might reverse, right? The battery is reversing the circuit, okay? Understand?
I don't know why it reverse.
Because the point has changed. The current changed direction. Like this one, okay? This one. So the energy flows, right?
This is so weird.
flows from this point. Okay, understand that?
The direction of the battery didn't change.
But if I collect another point from M, from point L, that create a net voltage, right? Create a net voltage. So and right now, because the M is not battery, okay? Because in the circuit there's no battery, no battery. This will be cancelled. If the point switch to the M from L, okay, there's no battery right now, and the capacitor will become a new battery, okay. There's no battery right now, and the capacitor this will be cancelled. If the point switch to the M from L, okay, there's no battery right now, and the capacitor will become a new battery, okay. Understand that? Becoming new battery, and this process is the discharging process. If the point switch to the M from L, okay, there's no battery right now, and the capacitor, no battery. This will be cancelled. If the point switch to the M from L, okay, there's no battery right now, and the capacitor will become a new battery, okay. Understand that? Becoming new battery, and this process is the discharging process. Understand that? Becoming new battery, and this process is the discharging process. Understand that? If the discharging process, so the current will flow in this way. Understand that? Flow to the emitter one.
Wait, why?
So
Why is the battery not there anymore?
because the point connect to the M. The point connect to M.
But then it's still in the circuit.
No, you look at the question. The observe if each emitter, if we continue the experiment by moving the collection X from L to the M, and this process will become the new process. The process is discharging, not charging process, which means
Okay.
that we have reached the maximum of discharging, right? And that becomes the discharging, right? Not charging. So we can regard the battery is not in the circuit. Okay. So the process will become discharging. We have reached the maximum of discharging, right? And that becomes the discharging, right?
Okay.
That we have reached the maximum of discharging, right? And that becomes the discharging, right? Not charging. So we can regard the battery is not.
What? Reach the maximum of charging. Now we're discharging, but the EMF doubled, so we should be charging even further. What is going on? What is going on?
Not in the circuit. Okay. So the process will become discharging, right? So when discharge the energy, the capacitor will become the C, okay, and the energy, the current flows like this way, right? Understand that? Okay. Understand that?
Yeah.
So the emitter, right? So emitter one. That has a large current right now. Yeah, in the opposite direction, right? Understand that? Okay, this is for emitter one. Understand that?
Yeah.
Okay, and how about the emitter two? Emitter two. Emitter two, it become what? Emitter two. Emitter two. Emitter two. How to describe emitter two?
The same.
It's the same with the emitter one.
Yeah.
Why? Because in the circuit, right? The emitter two, the same, so can describe in this way. Same current as emitter one. As emitter one, okay? Because this is the series circuit, right? Understand that series circuit,
Yeah.
right? So we have the same current as emitter one, and so it also choose a brief, right? Brief reverse current. Okay, understand that?
Yeah.
Okay, right. So we finished the question 3. Okay, the rest of the question you didn't work.
You didn't understand.
Okay. Next lesson, I will talk about the rest of the questions, and we are continue to learn a new chapter read about the magnetic field. Okay.
Yeah. Okay.
So next time, what time you're available?
Monday.
Okay, no problem. And you can use this notebook, and I think you can use the what have learned to interpret the question, and use what have learned in the question to retake or to think about this question. Okay.
Okay. Yeah.
Okay, I will send you. Bye bye.
Okay. Thank you. Bye bye.
Bye bye.
Okay. We are finally done. We're finally done with that. Now I just gotta do the questions and then do the questions and then find some questions online. I forgot how many questions. I got 12 questions to do. 9 questions.
熟是不？
咋？
立着呢。
The time constant. 5,000 times 0.37. 1,800. 3.5 milliseconds. Okay. Final question. The temperature difference between the plates of 220. We did a lot of questions. Let's check our email. April Fools. April Fools. Okay, okay, let's continue. Just had to take a quick break there. Where do I get the past papers? Where do I find the past papers, man? Whoa, 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 what happened here? Did my footage get deleted or something? Huh? What's going on? Whoa, 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 where's my footage? What happened here? What happened here? Man, I don't know what's going on, man.